Welcome back to High Performance Computing, Advanced Scientific Computing. The title of the lecture today is really Parallel Computing, with an interesting emphasis on parallel programming with MPI. So we will understand how actually parallel computing can be basically realized by really using parallel programming languages, libraries, and this has something to do with the message passing interface, which is the MPI abbreviation here. The standard for parallel programming, as we will see throughout this lecture. However, I also want to review a little bit what we had the last time. And this was a practical lecture 1.1, where we had a short introduction to C programming and also scheduling. We started essentially with understanding that many of the application challenges we have in engineering, in physics applications, is really about having lots of needs for computing. And we learned that basically for this, we need high performance computing. We also learned that essentially you have lots of these codes still being programmed in the C language. Some of them are even in Fortran. And of course, more recently, people have also used C++. And at the end of this lecture, you will realize some people use also Python nowadays with MPI for Pi, for example. However, the key essence to take away is that really this is a motivation for high performance computing. So we would not use these big systems just for Bitcoin mining, just for large banking transactions and so forth. So because of the large supercomputing centers that we have around Europe and US and China and around the world, mostly the need is really motivated by these scientific and engineering applications at cutting edge sciences also, but also of course the industry sector is very much using these systems for different applications, like in construction. You have already seen computational fluid dynamics, basically crashes of cars. All of this can be simulated. By simulating, we want to understand basically the application in question much better. That's why we're doing it. So we also learned a little bit then from the practical perspective how I should execute such a big application, which maybe requires many nodes, basically on a HPC machine. And we quickly came to the idea that we have a large area where here basically the groundwater modeling applications we basically introduced can be chopped down into different pieces. We call that domain decomposition. And this will be material also of lecture 3, much more in depth. But the idea is then really using different nodes on the supercomputer. But if you basically log in, as we have already seen in the practical lecture, into a HPC system, you're basically within the login node. You're not really on those nodes that should execute and compute all of this, what you have here, all the physics, complex derivatives, the message exchanges, the data. This is all basically something which you essentially submit to the login node, and then the login node basically forwards it directly with this specific commands that we learned to the scheduler. And then the scheduler really puts it on the concrete computing cores, which then execute essentially this application in parallel. Now, this in parallel can have different meanings, so essentially referring to, do I have lots of message exchanges between those, which is key of the lecture to understand today, or you basically just a high throughput job where you essentially have not much communication between those cores. But for all of them, if you want to use a HPC system today, mostly you will always find a scheduler. And the scheduler, let's say from the inherent design, is here given as an example. You see here the Juvels system, which is the top #1 system in Europe today, the biggest supercomputer we have in Europe. And you see here the different racks of the systems. And then in the racks, you have seen their node cards, and the node cards are then somewhere basically the different CPUs and GPUs and so forth. So the big system is broken down into many different pieces where different users use it at the same time, right? Not only you are using, let's say here in the example, 6 different nodes on the systems, also others use maybe 6, maybe 24, maybe 1,000 nodes in parallel. And with this, different CPUs, different GPUs, we will also learn a bit about the terminology in the next practical lecture of lecture 2.1. What is a node? What is really a task? What is a CPU? These are all differences in the scheduler we have to look much more deeply into. But for the first idea of really understanding this, this is basically something we will use again and again, no matter if it's Juwel, the largest system, if it's Jotun, our teaching cluster, or the deep system, we will also use in one of the assignments. So when you then look at this, how that worked from the kind of workflow, we S-batched on the login node, which means to the scheduler, a certain batch script, which had several, let's say, ideas how to execute essentially on this parallel supercomputer. This could be an application. This could be basically something which we just had, a little small hello world. No matter what it is, the same modus operandi as always. You have a scheduling script that you fill with what you want to do. Using here this interesting MPI run command, we will also allude to today more deeply into the lecture, and also, of course, in the practical lecture 2.1. You see, you have to load the right modules. We had done this in command line first, but if you have a scheduling script, it's very important to realize that we also basically there have to load all the relevant modules which are required by the application. When you submitted it, it's running on this interesting cluster and it's computing until it's finished and develops and creates basically then the application output and puts it into a file, which we have then seen here out of Slurm. And we could look into it. It is hello world. In other words, you don't have something suddenly as a screen and there's suddenly an hello world appearing. Some of you know Jupyter notebooks. You see the output sometimes immediately. Right here, it's different. In the batch system, in the scheduling system, which works really in a batch way, having always then this computing batches with workload to be worked on over time, means that you maybe don't execute right now. You could execute maybe in 20 minutes. It depends really on the schedule, on the batch queue, how full it is when you execute it. And you could look into this queue. You saw here was QStat. Here's an example of two my jobs. We have seen it last time. There's also a physics professor that at the same time was using Jotun. And this is reflecting that basically even the small systems have concurrent usage, like here the workhorse, the big one, the Jewels, and they are all having the very similar way of operating, which you should learn by this from the last lecture. And of course, we will basically go more deeper into this when we now think about, okay, parallel programming. This is now the next steps. We had the C program, we had scheduling, but we didn't really use hello world really deep in parallel, right? It was just giving it out with a kind of serial application. And we want to learn and understand what's now the difference between serial programming and parallel programming. What is it basically added value, but also the added complexity to this. So when we go for parallel computing and then we want to do parallel programs, there's essentially just two big standards you need to know. And this is the message passing interface, MPI for distributed memory, and also OpenMP, which we have in later lectures for shared memory. More recently, of course, if you do parallel programming, you would also say you need to understand CUDA, maybe for GPUs, which we also have in one of the lectures. But here we really focus on distributed computing concepts. And with this, address already some of the promises we did in earlier lectures, like in lecture 1, that we look more deeply in this distributed memory programming model. And this is really the message passing interface standards with certain concepts which stands the test of time. You will see these are kind of very much functions people have used basically decades ago, but more or less in the same way as we do it today. Of course, here and there, the operating environment changes a bit. The supercomputers advance, but the way how these ideas come with MPI collectives, for instance, with MPI point-to-point message exchanges, asynchronous and so on communication, basically remains the same because it's always needed by applications. And that's why we motivate a lot in this particular part of this application, again, with applications. So why we do this, why we need to do this in parallel. Then, as a more advanced topics, we already will understand communicators and MPI ranks to really differentiate the parallel processes. In the second part then of this lecture, we will just more look in this kind of programming basics. So what is, when we want to be starting with this, what we have to know from the environment, from the libraries, from the modules in a HPC system. Then, of course, we have to really think again parallel. That's always what you have to learn in this course. Remember, our idea is not that you become a really software engineering guru, a very good software developer here. That's not our goal. Our goal is really to understand parallel programming. Software engineering is taught in other courses. Programming is taught in other courses. Here we want to put an emphasis on parallel programming. Of course, here and there you learn something about code compilation and other parallel program building blocks like variables and so on. But of course, then the idea is really focus on the parallel part instead of making perfect code. And then understanding parallel executions, we will have several, let's say, simple applications that I will also more and more demonstrate throughout the course. And we will start at the next course lecture with practical lecture 2.1 again, where I will demonstrate you some of these MPI applications, which let's start with very simple collective applications, but then really have already like a ping pong application where you really understand then the message exchanges. Here's also an interesting video I brought in this last part of the second lecture where we will understand a bit the serial versus parallel application. And also when you think about that, the collectives have all specific aspects to it, and we will learn something about all gather. So for the learning outcomes, it is really something now of complex aspects of parallel programming. You will see having different processes in parallel suddenly. And if you then think about you want to scale all of this, maybe not just 4, not 8, you maybe want to have 256 in parallel running and use, or you want to scale across 1,000, of course, then you can immediately see there is some complexity in parallel programming that we will allude to today. We can also see that there are different abstractions. So when you go down from an application perspective, you maybe want to have an ocean simulated. So when you have an ocean, you want to break it into different tiles. When you have the different tiles of the ocean, you maybe want to do message exchanges of the amount of fish in the ocean, of the basically boat that goes from one tile to another one. You want to propagate a wave throughout the ocean, things you also will do in one of the assignments. But these are different abstractions on different levels. We will understand this more when we look into all of these applications in this lecture. And of course, then when you start really in scientific domain specific applications, you see here from plasma physics over to materials, and here basically also earth sciences again, you will see always similar scientific domain specific concepts, but also a specific foundation of parallel programming. So MPI is often used. A domain decomposition in certain elements is different used. These are also parts we will learn partly here. And with this, you really understand then, and coming out of this course as someone who can say, I can at least, roughly implement MPI here and OpenMP and understand how to deal with CUDA. So today we just focus on MPI. So let's go and let's understand it first from a perspective where you think about serial programming is something that we all probably know here. We have lots of concepts. There are arrays, variables. There are languages that you all know from C, C++, from Fortran to Java, and more recently Python is more used. They all have their different ways of working on it. Java as interpreter, Python scripting language, C needs compilation, and all differences. But still, their main paradigm is of course in computing in parallel and maybe doing threading or multi-threading on similar multi-core CPUs. But let's say we need much more to go really in parallel to a bigger problem that we will come to. There are different implementations, different compilers that make out of it, let's say, interpretable code in Java C, or the GCC, the GNU compilers. There are different, basically, implementations, of course, and also in this world of languages in serial programming. When we move a little bit to the message passing, to the MPI idea of parallel programming, and in general, a little bit the idea of parallel programming inherent, we will think much more of different concepts. We think about processes and send, receive messages. But of course, these messages maybe still needs variables. So basically, we don't get rid of all the concepts of serial programming. We rather add and complement a couple of things which we really require for our parallel programming. We will have collective operations. What happens if you want to distribute data not from one to another one in a send receive mode? Maybe you want to send something from one to many other tiles, which is important in some of the applications. Then we have different libraries, but all of them share the point that they are an MPI standard implementation. So there are different elements we will learn about the library of MPI and the various implementations, OpenMPI, what we use here in the course, but also like Parallelization MPI, which is in the deep computers. However, these are more or less, let's say, very dry elements of motivating the MPI usage. Let us look a little bit at an application example that will be also related to one of your assignments. So you see on the right, basically an ocean chopped down into basically 3D grid. And we want to simulate essentially this part of the ocean and want to see, for instance, what happens if we propagate a wave across time over those tiles. And this means it needs perhaps lots of computing. Also, when we want to add more and more detail, maybe the surface that you see here, or all the ships, the movement of fish, basically also weather, maybe that plays a role here. So more and more, let's say, added value maybe for the simulation. But you would start off thinking, okay, the wave doesn't stop suddenly, but just because I have another tile. But the other tile is maybe already on another processor, right? So it's not something I can just use my normal serial ideas of having a shared memory space where I then can just drop essentially the variable and say, this is my weight height here. Please continue with this weight height in the next tile. I have to send essentially the idea how high are the waves. Of course, you can imagine the more details you do, you will end up in physics. In fluid flow, there were different elements in physics we come to in one of the lectures, but you want to propagate the wave. And with this, you maybe leave the memory of one computer, of one process, where the processor is limited, and you use a communication network as we learned in distributed memory. Now, this is the idea how we want to do it. What could us help here in this regard? And this is really thinking about parallel computing. We think about that all of these, what I just said, these tiles have their life of their own. So this is here not a copy-paste error, if you may assume so. This is more want to illustrate that all of these tiles have their own processes in time, right? And they have their lifetime in time. In between, there should be certain message exchanges between them to maybe propagate the wave or having the surface simulated. And essentially what they do is to solve really a problem in a cooperative way. And this means the whole basically idea of this wave propagation. The other applications which you see here where we sometimes worked on, for instance, ice carving, where you have maybe sliding of ice down the glacier, which follows one particular MPI model of a glacier implementation or of ice implementation really. And then you basically have another kind of idea of another part of this application where we want to have then basically more an ice dynamic model, which is then basically have then the ideas how is a glacier end up essentially in the ocean, meaning really the carving maybe of big glaciers that you see here in the video, right? To understand this by research, we model this. And also by this, we need lots of message exchanges. You can imagine once the ice is in the water, it creates wave, it is flowing in the water, melting, and lots of these processes needs to be computed. So in the end, this means more physics. And, we have seen already from the practical lecture 1.1, last time we had this terrestrial systems, for instance, again, we said we're chopping it down to pieces and we can put it maybe on different processes because the computing is so intensive to compute all of this. So this is, of course, very much provided by the hardware. The computing processors are very good, as we learned, good single thread performance maybe. But what we didn't talk about is, so what is this message exchanges we talk about, right? So here means all the processes are in some way or another actually interacting with each other. And no matter where you go, in which domain you are, you will see many of these MPI applications are today in engineering and in scientific applications. We had also the neuroscience application with the Nest simulator, which is also using parallel computing. So when you abstract that a little bit, thinking about the lifetimes of the processors, here just example from processor 1 to processor 5, think about that we think about scalability in the thousands these days. Then you have, of course, lots of these message exchanges going wild back and forth. So you have to think about more structured way of doing it, where we then also will learn with the Cartesian communicator and lecture courses that there's a much more, let's say, principled way of doing it than just illustrated here. So it's much more an illustrative figure of telling you there are lots of message exchanges in these large parallel applications. So in a way, the motivation then is that we have always something to simulate over time. And for this, we use the computers. We have experiments on the one hand, which really we know from observing the nature, like for instance, here the bird, we know it's flying. So we need something like wings. That seems to be good. So this is something what we can actually create in the theory and create a model of the nature. What we can use essentially HPC parallel computing for is to bridge essentially these two pillars, right? So we want to have something over time simulated, the stress of the material, how much can I actually get into the air with a specific design of an airplane? What is the problem of turbulence, the sound that's coming out of an airplane? All of these questions are something which in theory is partly solvable, but to really better understand it and make links to experiments, it's really good to simulate that over time. And again, many of these applications are using MPI because they're very compute intensive, they're very detailed. It's not about gaming here to look good that an airplane is actually taking off. It's not an airplane simulator game. It's an airplane simulator to create a real Airbus, create a real, Boeing, whatever it is. But with this, there come lots of details, which requires really massive amount of computing. And the visualization is almost secondary. But of course, as I said, also in one of the earlier lectures, visualization is a very good helper really to understand these models much better. And when you go on, you will see also that actually not only simulation science is basically known physical laws simulated with numerical methods, so iterative concepts we will come to back inside this course. We also see more and more that data science applications using HPC. I was saying a lot about deep learning in the beginning, so this requires GPUs. But here you find also examples where MPI is used in order to do clustering. So this is a very highly scalable HPDB scan implementation from one of my PhD students we still support. And you see with the number of cores, it really can have a significant speed up, where here, for instance, we have a point cloud, which was not basically visible with any buildings. The buildings comes when you cluster data together, so that the closer the points get, they create a building. And you can imagine that, here recreate a whole city of Bremen in gigabytes of data is already quite challenging. So you use computing and high performance computing a lot for this, and with this DB-scan clustering algorithm, which we will have also, of course, in lecture 10. So we will have this much more in detail as here. But then also when you think about you want to do this over whole countries, maybe here's part of the Netherlands, and it's really essentially all over point clouds over the Netherlands that we could use for clustering and understanding the situation. And with this, you really need HPC as well. Another example is here when you have high resolution images of the human brain cutted, and clustering is to find out these different cortical layers with different functions of the human brain really. And of course you do this in 3D, so this adds complexity. And also here you could use clustering, for instance, in this 2D setup to understand the different, let's say, similarities in different layers, making and marking them as different layers. But I will come to these examples back. I just want to say that for this, we use the DB-scan algorithm based on MPI and even on OpenMP. So you see here the notion of hybrid that we will also come back to in later course hours, meaning here we combine the power of MPI and OpenMP. So motivated by these applications, you realize and remember we had Deepest, one of these projects which develops these new supercomputing ideas around modular supercomputing architectures, where all of these different applications are just making examples from, where giving his input basically, or their input to the design. And what the design was is essentially is a cluster module here, with high single thread performance. And here we could see that many of these applications running here actually take advantage of MPI. Just to bridge a little bit now from the application again to the HPC concept, right? HPC concept means I have lots of cores that I want to use in parallel now, basically on such a cluster module. And the second part, what we want to have is, we want to have this not, let's say, for the current moment, we want to simulate something over time, like the race car going through the air. How can we improve maybe the engineering with this car? What is about the heat dissipation in a room? Can I actually simulate this? I don't want a situation right now. I need it basically now maybe to understand what's happening in the future. But here I can simulate and predict a little bit what's happening in the future. We see simulations. And this is exactly the idea. Now, you would start with a good parallelization method, a domain decomposition we will come back to in lecture 3. Then you would start and write some good MPI code using lots of these libraries, which are today already existing for many of those problems. And then you will use basically kind of all the time iteratively a concept we would say integrating more and more the technical code with the problem domain code. Technical code means in this position MPI, this message exchanges. But of course, we don't do this for fun, just exchanging messages. They should have some domain specific part of it. Like basically we want to understand how it affects maybe the tires, the faster you drive. So these are things where really the idea now comes to mind that we have to exchange variables of this domain specific data between these different processes, maybe to compute different things, maybe to represent basically different parts of a race car. And the end, you need something like a protocol, a language that enables me to send from one processor's memory space to another processor. And this is I do basically via a network interface, which is always very much given. If you remember in the first lectures, I would make an emphasis on this network interfaces here, on very good performance on them, which is basically then an important part today. Of course, as I said, this is a little bit in a simplistic view here. I say the setup is rarely used. Today, people using it with OpenMP together, they would have other concepts basically of having a much more hybrid setup. We have GPUs today, which maybe also take part of the computing. But this is more the first, let's say, idea how you come closer with the MPI paradigm. I was already saying it's a standard of the MPI forum. So basically there are lots of these MPI implementation that exist already, but you can say that the send receive would be almost every time the same in different implementations. So you can assume so. Even if you go across languages, you have C, you have Python, all of them share in common the way basically how send receive as one example only is implemented. You would say it's a sending to another processor. But if you think about that, they all have their lifetime on their own. You can imagine that if this processor here, the second one, is not really actively listening of receiving something, then it may be just computing and ignoring the message, so to speak, right? So bluntly speaking, we always need, if we want to send already someone who is ready for receiving something, send something about the ball play between two partners, and the one is drinking coffee, and the one that throws the ball is actually knocking off the guy with the coffee in the hand because he was not ready to receive the ball. He was having a process drinking coffee. So with this, the general principle remains that you have to think in parallel. It is not enough to think that this program will be executed many times and then I do it automatically in parallel. It's not working. In this sense, we have to really have parallel algorithms which take care then of this OpenMP implementations in order to have these message exchanges implemented. Of course, it's the beginning of a whole course. So here and there, you would still thinking about, okay, what happens if we both send at the same time? What happens if everybody receives, no one sending? So they're all questions we will come to in performance analysis, or if I wait forever receiving, and actually there's a late sender problem and so on. This is a really notion we will come to in later lectures. Here you always think about, from a technical perspective, how I can communicate. And there are around at least basically 12 functions you should know by heart. MPI broadcast, MPI altogether, send receive here and there is still, of course, also used. And it's actually not much, although the standard has many, many, many more functions to really fine tune your applications if it needs to be. We have links to parallel IO data, right? Very important part of it. We will come to it in one of the subsequent lectures. You have lots of different ways of communication, right? We will come to collective communication, we come to point-to-point communication, and finally, we are very interested on the application on the supercomputer, which is beautiful in a way because it enables really portability to go between the different supercomputers, because most of them have always MPI. Of course, here and there are different implementations or different versions, but the same concept apply, which is very important to us. Right, when we think about portability, That means essentially that we can take already with an MPI library 1, let's say here an MPI implementation MPI, or another one HPC machine B, which has a parastation MPI, could be our ULIF systems here. And you basically have the race car simulation already in MPI. You can almost for certain assure that the MPI, when you're compiling it, will relatively good work. With relatively good, I mean there's always certain elements in the system which might be still required to change. Let's say how many tasks per node you can execute. Things which will become much more clear when we have practical lecture 2.1. In the theory, it's a bit hard to understand that, of course, these HPC systems never look completely equal. However, the whole language idea of using MPI with your own language programming in C and so on, and then with the domain-specific code will not so drastically change, rather how you really basically take advantage of the different HPC systems. So with this, MPI really over the decades now is a very stable standard that you can also be almost certain that it's enable portability, at least to a significant fraction. On the other hand, I also want to basically show you a little bit where MPI is not useful. And a big example is the internet, right? If you now think about, oh, Morris tells us how to create a new chat client and do something like a dedicated communication network protocol, which I can use in the internet, something like TCP, IP, and so on, and the securities about HTTPS, you will really have not the right idea of using MPI. It's really a goal here to simplify the parallel programming within one computer and within one supercomputer, because it has very many of these processors that can actually run processes with their lifetime, as you see here, over time, and then communicate each other. There's no security. Basically, it's a very much optimized protocol, assuming a secured environment. Hence, you remember our modular supercomputer there, it's not completely true. We go from a cluster to a booster module, also with MPI, with a specific type of MPI we implemented there, but still we assume that the whole system is already in a specific security zone. You already basically don't need a kind of HTTPS for it or some other secure mechanism. With this, it's very important to understand this. This is already time also an exam question. Let's come a little bit to an example. Message passing exchanges with data. You have here a typical send receive. I think now I come through a couple of them just to explore a little bit what that means. You have some data from one memory space, you send it to the new one. It's a send, and we call this point-to-point communications, right? But as I said, the counterpart needs always to be ready to receive. So broadcast is now the first collective function we will basically look into. Collective means we have more than one processor involved. And of course, then with this, the idea is really to use one-to-many. I always basically show it here in the next couple of collective operations here on the top, what it essentially means. Here, if you have an example of the broadcast operation. And all of these collective functions you need to know by heart. It's very clear that they will come in the exam. So also basically focus on the learning on these collective functions, but we will also learn them throughout our assignments, our practical work. But this is a very obvious one. You have one data item that you really send to different processors. Now, if you remember, it's not a direct, correct picture. It would always go through the memory to the memory of the other one in order to do something. And basically, there could be already some other data stored here. It doesn't matter. You send something, and in the program flow of the second, they will receive it. And I have just one function. This can enable it, the broadcast function, and will automatically distribute it to all of those which are on the same communicator. And we will come to the communicator in a moment. So when I have another collective function, it's scatter. You can imagine that you may have an array and you want to send it from one processor again to many others. You want to scatter essentially an array. And this is an operation you can do. You will see if you have this array here on one processor, you chop it down automatically with this operation and then send it also to the different processors, something also used in many of the basically different applications we have. Mostly it's around that you want to scatter different data. It's a kind of important part, maybe differentiates it from the broadcast operation, which is often used to distribute the same data maybe to many. Then the gather process is also incredibly often used. If you think about that, all of these processors have computed variables differently and basically on the context, environment, the waves on different heights, whatever it is, you basically do. But you want to have maybe an end results at the end, then you basically always come to something we call the gather operation. They have worked independently for a certain while, and now they want to come many of those all to one processor that then has the output. In the end, basically, you can say this processor is collecting the results from everyone and then wants to do something with it. Maybe an average, maybe this basically a simple sum. It basically is not inherent in the gather, but here it's basically from many to one. Now, the interesting thing is that usually you want to do something with this, and why not doing it directly and reduce the source code lines when you know already that you want to do simple, let's say, math operations. There could be a minimum, there could be a simple sum, you could use a maximum, a product. There are a couple of those which are already defined. Here's a global sum as an example that enables you to actually combine this gather that you just have seen with a mathematical operation that already, for instance, here gives you the new value sum up between all the different ones, including your own, actually in the part of your parallelization strategy already as a kind of interesting sum about this. So you see, it's really a practical perspective of doing parallel programming, and it should be, because MPI is used in parallel computing incredibly often, because of course it's straightforward how you would use it for a practical application. Of course, we said now all the processes needs to be always involved when I said about broadcast and gather and so on. But that's not completely true, because what you can do is to create different communicators, and we will do this in later lectures. The first communicator you will always know in MPI is the MPI Comworld. It's a specific communicator which includes essentially all the world of all the processors. This is, of course, basically something for very simple applications, what we will use in the beginning. So every time you see MPI Comworld, you can imagine this is all the processes we got assigned from the scheduler, what we asked the scheduler to assign us, which we will see much more clearly in practical lecture 2.1. But then you basically can address with broadcast, and you use this communicator, all of them. You also see these different numbers, which is the meaning of a rank. The rank means, from MPI perspective, that it's a unique process. That means every one in this specific world of communicators has a specific rank, and you can have different ranks because you can have different communicators, something we will talk about. But here essentially you see with rank 0, I always know it's this specific processor, and you can see they all have the dedicated numbers. However, we will see in subsequent lectures that you can maybe create different groups. You get this assigned, the MPI Comworld, all this kind of 10 processors here, 0 to 9, but maybe you don't need all the 10 for the application problem at once. You maybe want to simulate different parts. And as an example, I brought you here again the idea that we already know now, the ocean, the propagation of waves through the ocean. That could be part, let's say, covered by 5 processors and a different group of communicators. So you would create a second group out of Comworld and create a second communicator that only involves those processors, which really then basically send messages across with the waves, essentially. But then you have also, of course, new ranks for them, and they would heavily interact basically on the elements of physics here, how waves are propagated. Now, on the other hand, you also want to simulate something where maybe you want to have an interaction with the ocean. Or let's imagine you have the shore and there is a boat and someone is sailing, let's say, across Iceland, basically, and we want to just simulate the interaction of the ocean with this boat. So there you have different parts of the boat. You have the basically boat structure, you have maybe the wind that is influencing the sailing strategy of this boat here, going to the left to the right, influencing then different ocean parts. So here you would first basically really use the wind interactions with the sailing in order to define the direction. And then you would communicate with the other group and really to understand how this is affecting my height of the waves. How is this affecting in the next time step now the position of the boat? Because the waves influence the position, but also the wind And the sailing boat, of course, is influencing the next position of its own. So these are the things we want to do with MPI ranks and with the communicators. And will come clear, of course, when we have also more advanced lectures and practical examples. And this is really all I wanted to leave on the table for you for the first part. From the theory, I brought a small video that, in my opinion, captures nicely several different aspects. For instance, a gather all or all gather that I didn't capture yet. And also the idea that it must not be C or Fortran all the time. Even Python has with MPI for Pi now in MPI implementation. So let's have a look on this video. Okay, so much for the video, and see you back in the second, where we look a little bit on how we will create our own parallel program.